In this video lesson, we are going to learn about something called Gibbs free energy and how we can examine whether or not an equation or reaction is going to occur spontaneously with some measured values. We've already studied a little bit that spontaneity is dependent on two factors. It is dependent on delta H, which is the change in the enthalpy. It's dependent on the change in the entropy of the reaction. And then we also have noticed a third factor that we're going to quantitatively tie into this is the temperature that the reaction takes place. Well, delta H, enthalpy, delta S, entropy, and T, temperature, all are factors that tie into something called Gibbs free energy. Gibbs free energy is symbolized as a delta G. It is the energy available to do work in a chemical reaction. The mathematical equation that we can quantitatively evaluate is delta G is equal to the delta H minus the T delta S. Okay, and so just a reminder, if delta H is a positive delta H, then we know we have an endothermic reaction. If we have a negative delta H, we know that that is an exothermic reaction. We know that when a reaction is exothermic, we know that that is a favorable condition for spontaneity. And if a reaction is endothermic, that is not favorable, that the reaction will be spontaneous. Delta S. If the delta S is a positive delta S, that's an increase in entropy, right? That's an increase in disorder. Or we can have a negative delta S, which things are becoming more ordered. And we've seen that an increase in disorder promotes the possibility that a reaction will be spontaneous. So those two factors work together, and but we're going to see how temperature ties into this. Now, temperature is always going to be measured in Kelvin, and the interesting thing about Kelvin is that Kelvin is always a positive number. You can never have a negative Kelvin temperature. All right, so this equation factors in temperature in addition to the enthalpy and entropy changes that we've already examined. So we could plug in numerical values for delta H, delta S, and T to get a value for delta G. But what we're going to emphasize that it is the sign of the delta G that's going to determine the spontaneity of the reaction. If you calculate a delta G and it's a positive number, we absolutely know that that reaction will be not spontaneous. If the delta G is negative, then we know for sure absolutely that reaction will be spontaneous. If the sign of the delta G is neither positive or negative and is just 0, then we say the reaction is spontaneous in both directions, both the forward and the reverse directions, and therefore the reaction is at equilibrium. Okay? So if we were to plug in values for H and S and T, it's not necessarily the value, the number that we come up with, but if there is a net negative number as a result of solving for delta G, then we know that that reaction is going to be spontaneous. So let's take a look and see why this is the case mathematically. Let's say, case number 1, we have an endothermic reaction, right? If we have an endothermic reaction, then we know that the number we're plugging in here for delta H is going to be a positive number. If we know that the entropy is decreasing, or is a negative number, right, then this value right here, this delta S, is a negative number. Okay. Now, let's see what happens when you factor all this in. The first thing you'd have to do is if you multiply the temperature, which has to be always be a positive number, if you multiply the temperature times the disorder value, the entropy value, positive times negative, right, that's always going to give you a negative value. So I'm going to put that down here. So positive times negative results with you having a factor. This factor is a negative number. Okay, but now what happens when you subtract a negative number, right? You subtract a negative number, you're going to always end up with a positive number. Okay, so in this case, this whole factor, all told, is a positive number. So if delta H is already positive, and now you're adding a positive number, right? We know that that delta H is always going to be a positive number, which means that this reaction is never spontaneous, which you could have predicted anyway, because an endothermic reaction is not favored, as we learned in our last lesson. A decrease in entropy is not favored, right? So we actually didn't need to do the math or to follow through what's going on with the signs here to figure out if it's spontaneous or not, because we already knew these two factors, neither one of which is favored towards spontaneity, that's going to predict that it's just never going to be spontaneous. So let's take a look and see what happens in the other scenarios. Okay. Here is a scenario where we have a negative delta H. It's exothermic, right? We know that this is favored. And we have a positive delta S, more disorder. We know that that's favored. So we're going to predict that the spontaneity should be spontaneous. But let's see what happens when we manipulate those signs in the equation, right? So if we say that the delta H is a negative number, this is a negative number. And then we know temperature is always positive, and now we're saying that the entropy is a positive number. So let's see what happens here, right? When you multiply a positive number times a positive number, this whole unit here is going to be a positive number. But then when you subtract a positive number, that's going to be a negative number, right? You're going to subtract a negative number. But you were starting with a negative number, and now you are subtracting out this number. So there's no situation where this overall, the delta G, is going to have to be negative. You're going to end up with a negative delta G. And we know that this is always spontaneous at this situation. Okay. Case number 3. If we have an exothermic reaction, which we've already said is favored, but a negative delta S becoming more orderly is not favored, then the sign of the spontaneity, we've been saying that sometimes spontaneous and sometimes not, but we're going to figure out now when it's spontaneous and when it's not spontaneous. So let's follow through with the math here. We're going to make this delta H a negative number. So that's a good start for delta G to be negative if you're already starting with a negative number here. And if you're already starting with a negative number here, you want this to be a relatively small number. Okay, so let's see how we do that. If we have an entropy that is negative, right, so when we multiply these two things together, that is going to be a negative number. Positive times a negative is always going to be a negative number. But if we are then subtracting a negative number, you're actually adding a number, right? So if you have a negative delta H, and then this term is positive, how do we ensure that this delta G stays negative? Well, to do that, we have to make sure that temperature is a small number, because if this is a small positive number, then this number will help keep delta G to be a negative number. So delta G will be negative when we are at low temps. But if the temperature is big enough and makes this whole unit here, this whole value here, a larger number, right? If you have a negative number and you're adding a large positive number, then that's going to flip the total result to be a positive number. So this is the case where the sign of G will be positive when the temperatures, when you have high temperatures. Okay, so this reaction will be spontaneous at low temp, and in this situation, it'll be not spontaneous at high temp. Okay. All right, let's take a look at the last case. You might see where this is going, but here we have an endothermic reaction that is positive delta H, so that is not favored, but it's ending up with more disorder, so that is a favorable situation. So when you have one factor favored and the other not, then we know that the spontaneity is going to be sometimes spontaneous, sometimes not. So let's figure out how we can know when it is going to be spontaneous and when it's not going to be spontaneous. So let's start with the math. If we start with a positive delta H, well, remember the goal for spontaneity is a negative delta G. So if we're starting with a positive number, that means this is going to need to be a big number. So let's follow through. We said delta S is a positive number. So a positive times a positive means that whole unit is going to be positive. And if you are subtracting a positive, right, then you are truly working with a negative number. And so here's the idea that if you want delta G to be negative, this whole unit has to be big enough, right, to make the delta H, to overcome the lack of favorability of the delta H. So we would say delta H would be negative at high temperatures. So spontaneous at high temperatures. And the sign of delta G would be positive at low temperatures, which means it would be not spontaneous. So the idea here is that there is an interplay using the Gibbs free energy equation of delta G equals delta H minus T delta S. There's three factors: delta H, the enthalpy of the reaction, the temperature that the reaction is happening at, and the change in the disorder of the system. Mathematically, if we can manipulate or evaluate those three values, we can determine the overall value of delta G, and most importantly, the sign of this delta G, right? If it's a negative delta G, we say the reaction is spontaneous. If the delta G is positive, we say it is not spontaneous. Okay. And so that is how enthalpy and entropy and temperature all factor in to determine spontaneity by evaluating the equation quantitatively. You'll find on the problem set and the practice that we will actually substitute numbers in to give you some quantitative practice with this concept. So that's it for now. We'll see you back in the classroom.